Good afternoon, everyone. Thank you for joining us today. Welcome to the Water Research Foundation webcast for Project 5156. And the project title is Occurrence of the Legionella pneumophila in Drinking Water Distribution System. I'm Grace Zhang. I'm a research principal here at the Water Research Foundations. I'll be your moderator for today's sessions. Well, before we get started, I would like to quickly go over a few housekeeping items. So if you have any questions during the presentations, please feel free to type them into the question box. So we'll have a Q&A sessions at the end. And if we don't get to all of your questions, we'll be sure to follow up with the answer after the webcast. And the slide and the recording of today's sessions will be available on the Foundation website. You will also receive the certificate of the completion automatically after the webcast. At the end, we'll really appreciate if you could take a moment to fill out a short follow-up survey, so your feedback help us improve the future webcast. So we have a lot to cover today in just 90 minutes. So I don't want to spend much time on this slide, but just wanted to let the audience know that the Water Research Foundation has excellent resources on opportunistic pathogens, covering topics like communication, and analytic method, and sampling and monitoring. So all of these projects I'm showing on this slide, we had a webcast previously. So you can access the webcast recording and the final report from the Foundation website. So today we're going to share the project 5156 finding and recommendations with the audience. So again, if you wanted to see the more detail of the projects, please head over to the Foundation website and enter the project number 5156. Then you can find the full project details. So now I would like to introduce today's speakers. So our first speaker is Dr. Tim Bartland. Tim is Executive Director and a Research Engineer at ASPRI, the Environmental Science, Policy and Research Institute. ASPRI is a nonprofit dedicated to the water quality research, working to bridge the gap between the water utility and their customer. Tim has been with ASPRI since 2016, and his research focused on controlling opportunistic plumbing pathogens from source all the way to the tap, and as well as studying how water quality changed within the building plumbing system. And then our next speaker is Dr. Marc Chevalier. Marc is principal and manager of Dr. Water Consulting after retiring from American Water. Marc has authored over 300 research papers and has earned numerous awards for his outstanding contribution to the water science. He currently serves on US EPA Science Advisory Board and was part of NAS Legionella work groups. Marc is also the fellow of American Academy of Microbiology and National Academy of Engineering. Our third speaker is Gary Burlingame, and then Gary's retired from the Philadelphia Water Department after more than 40 years of the service. Now senior scientist at ASPRI, and then Gary's expertise covered a wide range of the area, including drinking water regulations, managing aesthetic water quality, and the distribution system monitoring, and the laboratory management, responding to the customer complaint, and the water safety planning. He has been widely published in journal AWWA and Offlow, and continued to volunteer with the Water Research Foundations. And then Dr. Jen Clancy is not presenting today, but we wanted to acknowledge her as co-PI of this project. So now I'll hand it over to the team. Team, please begin.
All right, thanks a lot, Grace. First and foremost, I have to acknowledge the many contributors to this project, and most of all to the utilities who conducted monitoring and participated in this study. It was a long slog for them. It was 2 years worth of sample collection, and there was a certain amount of courage involved in this too. This Legionella, as everybody knows on this call, is a new frontier in water quality management, and it took a little bit of courage, or a lot of courage, for the utilities to participate. So we thank them very kindly. Our project partners included IDEX, and they were very generous with the with participating and bringing materials to bear. Q Laboratories, they did a lot of in-kind work as well as other work, and you'll hear what that was. There are two contributors, two partners that we won't be able to talk about the results today because we didn't give them enough time to finish their analyses before we submitted this final report. They are the US EPA, Helen Buse and Jeffrey Szabo, and Georgia Tech, Amit Pinto. Co-sponsoring agencies were AWWA and ASDWA. Our scientific advisors were Ken Rodert and Clarissa Lucas. We had an outstanding project advisory committee, very committed people and very prompt and with great comments, and we're grateful to them. And then the WRF staff, Grace was the project manager, the project coordinator, Karina Santos, and a special shout out to the communications and marketing director and content lead on this, because they helped us finish this project in sufficient time to contribute to other efforts that are ongoing. All right, so I'm going to start with the introduction and project overview, and that starts with why Legionella. So we're doing Legionella monitoring occurrence in the United States. Well, why are we interested in Legionella? To most of you, the graph on the right is going to be familiar. That's from CDC. You can see that Legionnaires Disease in the United States is on the rise. Although interesting things happened during the COVID pandemic, but we're not here to talk about that. Legionella is important because it causes Legionella or Legionnaires disease, which is a serious disease with a high mortality rate. There's a big public health cost and impact. Some Legionella species also cause Pontiac fever. It's a milder disease. Generally, the prevalence of that isn't known. U.S. outbreaks are more prevalent in the U.S., eastern U.S., but you'll see in other information that we present that the bacteria are elsewhere. Outbreaks have occurred in surface water and groundwater systems, public and private utilities, large, small, and medium systems, i.e. everybody is impacted by this. So that's why Legionella. Why now? EPA has recognized for quite some time the importance of Legionella, and they're reviewing the microbial and disinfection byproduct rules and assessing whether revised rules can better protect public health with regard to Legionella, among other things. Their working group had a number of Legionella-related recommendations. They recommended a numeric minimum disinfectant residual requirement, and we'll talk about residual and how it's related to Legionella today. They recommended a national building water quality improvement initiative, and that recognizes that Legionella is both a drinking water and a building water problem. They had a couple other recommendations with regard to storage tanks, and water quality improvement and regulatory compliance for consecutive systems. But EPA has a big challenge here. Let's be empathetic to the regulators. There is a near absence of Legionella data to really inform how improved regulations can better protect public health. And that's where the Research Foundation stepped up and supported this project to generate some of those data that will help inform good regulation. All right, I'm going to spend probably a little too much time on this slide, but I think it sets the stage pretty well for what we have going on. This is in risk assessment, you would call this the exposure pathway. So Legionella, they're in groundwater, they're in surface water. They're plentiful there. There's natural occurrence. They come into a water treatment plant, and they're generally reduced to below detection. And you would think, okay, fine, we've solved the problem, but we really haven't solved the problem, because there can be some breakthrough of water treatment. A number of studies have demonstrated that, for example, if the bacteria are in encysted amoebae, they can break through treatment and get into the distribution system. Once in the distribution system, they can either just survive, they can hang in there at baseline conditions, and we'll talk about what baseline is, or they can grow depending on whether sufficient barriers are in place. But generally, the numbers in the distribution system, as you will see in this study, are quite low. they are not zero though. The water isn't sterile. So the distribution system will periodically seed building systems where this is the decisive part of the risk, the risk exposure pathway. In the buildings, they can survive. They can also amplify. The conditions tend to be better for amplification there, and that's where human exposure will take place. The challenges to Legionella risk management here are that, number one, they are manifest in the risks are manifest in buildings and outside the control of the water utilities. There are things water utilities can do, but they cannot do what the building community would like, which is to serve sterile water with no organic carbon to the buildings. This is not possible. We all know that. This is kind of on the wish list of the building community, but it isn't going to happen. And periodic seeding does happen. Another thing that makes Legionella tough is that the exposures are through breathing. Jen Clancy likes to say there needs to be a Safe Breathing Water Act. And these pathogens are different from the ones that we're more accustomed to dealing with because they're inhalation risks. They're a problem because they pose a latent risk. What does that mean? It means that they're present at some kind of a baseline level, both in the water distribution system and building systems, and they're just waiting for the conditions to become right to amplify. That doesn't mean, hey, multiple barriers doesn't work. It means that we have to have different multiple barriers, and they need to be applied differently and perhaps more consistently. Legionella management is going to be a team sport. It has to involve the utilities and the building water systems. You can see that the utilities right now, they have water quality management, regulatory compliance, but there are things that utilities can do to improve conditions in building systems, but there is a limit to what they can do. On the building side, water management programs are increasingly being developed and applied, and between those two elements, that's how Legionella risk is going to be managed. And there needs to be some education component too, and research such as the Research Foundation has supported. And all buildings are de facto consecutive systems. I put that in there because this community, we're the drinking water community. If you think of the building as a consecutive system, that might help you understand a little bit better what you can do in terms of keeping the water quality good and helping the consecutive system manage itself. So the project objectives were to develop a response and communication protocol that utilities can use following Legionella pneumophila detections. Gary Burlingame will talk about that. This is a critical step. We would collect data to characterize the relationship between Legionella pneumophila occurrence and concentration and disinfectant residuals, and I'll throw in temperature there too. We would analyze those data and then also do a benchmark risk analysis of Legionella pneumophila and distribution systems, and Mark will be giving you the results of that risk analysis. This is intended to help us assess the value of monitoring, to develop a fully characterized data set for use in microbial and disinfection byproduct rule revisions, to identify approaches utilities can use to provide the highest standard of care in Legionella management, and also give us, sort of scientific or knowledge on the occurrence and nationally the occurrence and what changes the occurrence, what type of systems are how different systems differ with respect to occurrence. What do we expect out of well-run utilities? The project then, the overview, we first, and this was primarily Mark, recruited utilities and offered training to the laboratory staff. They were given training we had workshops to help decide how positive samples should be addressed. We developed and disseminated the protocol that came out of those workshops. Then came sort of the center point of the project, monitoring, analysis, and data reporting for Legionella pneumophila, and Mark will walk you through that, data analysis and reporting. Just a quick, you'll see this slide again in just a moment, but the workflow, the yellow panel shows kind of the primary analyses that we did. Samples were collected by utilities, analyzed using the Legionella assay that Mark will describe. describe. And then there were some follow-on analyses that were done so that we could develop, additional scientific information about the positives that came from the utilities. There were a couple of additional analyses that are not going to be reported on here, because we didn't give the researchers sufficient time to get things done within the time frame of the project. The US EPA did sequencing of of some of the isolates that came from the primary analysis. Georgia Tech did some community analysis work of whole water samples, and then we did a side-by-side comparison of different methods for detecting Legionella. So that introduces the project, and I'll hand it over now to Mark to talk about monitoring and methods.
All right, thanks, Tim. Well, as we've already kind of alluded, we had 57 utilities that volunteered to collect 3 samples a week for 12 weeks during the summer months, because we had previously shown that, we know that Legionella is a organism that grows in warm temperatures, and we don't find much amplification during the winter. So we target our resources during the time that we expect the Legionella to be most prevalent. And utilities did this for 2 years. So, second to Tim's kudos to the brave utilities stepped up and did this. The map shows that we had representation north, south, east, and west across the country, and included utilities of various sizes, mostly large utilities, large and very large, because they more participate in research. But to the credit, we had some medium and small utilities. We had about a 40-60 split between free chlorinated and chloraminated systems, and because of the kind of larger utilities, we probably had a weighted to more surface water, but also utilities that had a blend of waters, groundwater and purchased surface water. So pretty representative of a snapshot, particularly of probably more Research Foundation subscribers than necessarily completely a sampling of all the utilities, but enough to give us kind of a insight into Legionella occurrence in water systems. And as Tim had alluded to, I'm going to talk about these 2 sides. First, let's talk on the left side what these utilities did. They collected and analyzed samples for Legionella pneumophila using the Legiolert test. The sample locations were largely left up to them. We asked them to choose sites that they thought were more likely to be positive for Legionella, that is, tend to have low chlorine residuals. We had some of the chloraminated systems specifically go out during nitrification events when they knew chloramine residuals were low. So the utilities did a really good job knowing the systems and trying to find the more problem areas. Most of them did the analysis in-house. We had 2 utilities that sent their samples to a commercial laboratory for Legiolert analysis. And then we had a few utilities that had ongoing samples, and they provided us that data set. So the combination of active monitoring and historical monitoring, all using Legiolert, allowed us to generate this data set. So we talked about Legiolert. In case you're not familiar with it, it is a liquid media that grows Legionella pneumophila, and it uses this quantitray, which generates an MPN, a 96 well MPN. So but that MPN is equivalent to a plate count for all intents purposes. And so the utility would count the colored wells within that tray. The way the sample collection is done, the utilities collect the sample. They have to check and adjust the hardness if necessary. Then they add the secret sauce, pour it into this tray, put it in a kind of a fancy sealometer, and then incubate it at 39 degrees. So the big thing to get the utilities up to speed on this, they had to have the sealer, they had to have a separate incubator from their routine total coliform analysis. But by and large, most of them, this was something they could easily do, and so we accommodate that. More details are available in the report, but just sufficient to say we, as a project, we had the utilities send those positive trays to Q Laboratories in Cincinnati, was kind of a reference laboratory, and their Q Laboratories opened the trays and analyzed them for detection of Legionella pneumophila within the tray. And overall, when we did that analysis by qPCR, 96% of the trays that we could ship and analyze quickly, we had Legionella pneumophila detected in that. And just to show you here, pictures of 4 trays that did not have Legionella pneumophila detected in that. On the very left-hand side, on the very right-hand side is a positive control. You can see that kind of brown colored reaction. We had 2 that are immediate next to that kind of had a light colored reaction. So, you know, our experience is that this is probably not a sufficient color enough to be positive, but we had the utilities send the analysis, and we didn't detect Legionella pneumophila in that. The second from the left is kind of an unusual, kind of really almost a black colored. That's unusual. We didn't find Legionella pneumophila in that. But on the very right-hand side, I'd have to say that kind of straw color there looks the same as a positive control. And but for whatever reason, we didn't detect Legionella pneumophila in that tray. So for our research project, we scored that as being a 0, a non-detect. But all in all, even if these trays were counted within the project, most of these negative samples had very low MPN values. That far right one would only be MPN of 1. So it made very little difference in the overall occurrence or overall concentration, by the fact that for our project, we wanted to detect Legionella pneumophila within the trays. Let's talk a little bit about that right-hand side, and that is the split samples. So for, and this included, I'm sorry, I think I went, yeah. This for 8 utilities that had some positives in the first year. In the second year, we had them send water samples to Q Laboratories that did side-by-side analysis. Now, the utility did the Legionella test. The Q Laboratories did the standard ISO 11731. It's the standard method. It's a plate count method for Legionella, as well as we also did a viability qPCR test that measures not only Legionella species, but Legionella pneumophila serogroup 1 and the other serogroups of Legionella. So there were 143 samples split between these 3. And I just show here for the qPCR, it was a commercially available microproof. It's marketed by Hygienia. At the time when we started the project, it's a European-based test, but also they have an add-on to that to do a viability test. And because we knew we were testing waters in chlorinated systems, it was important to us to be able to have a comparison of viability qPCR versus our other culturable methods. So those results are shown here. Of the 143 samples, we had 3 positives for Legionella pneumophila, 1 by Legialert, 2 by the viability qPCR test. Interestingly, they were all in 3 separate samples. So that happens when you have low concentration Legionella and you divide it up, it's going to go into one test or the other. So not a big difference between these 3 different approaches for detection of Legionella pneumophila, which is kind of a surprise because there's always this kind of assumption, well, you know, molecular methods are so much better and you'd have to be, you know, why are you even bothering with culture methods? Well, lots of different studies have shown that detection of Legionella pneumophila by the Legionella is a pretty good assay and one that's capable for utilities to do. I want to draw attention here now to the positives by Legionella species. So both the ISO method and the qPCR method could measure Legionella species. Legionella just measures Legionella pneumophila. And in the water systems, we had 37% of the samples positive for Legionella species. So Legionella species are far more common in water systems. And in fact, the 3 samples that were positive for Legionella pneumophila were negative for Legionella species. So monitoring Legionella species really has a pretty low value as a predictor of public health significance. And when we compare these to other published results, the Regi, apologize if I butchered your name, and also Wang study, when they did just now straight PCR, not viability PCR, they got 85% positives, plus or minus, of Legionella species detected in public water systems. So public water systems, as Tim said, Legionella, this is their home. This is their natural aquatic environment. They will be present. But Legionella pneumophila is present here at much lower levels and less frequent. And our goal from a public health standpoint is to kind of manage their occurrence. So, and then we found that that the ISO method only had 1 sample that was positive for Legionella species, even though it's widely kind of said it can measure all Legionella. So little value in using the ISO method for measuring Legionella species, and little value of that as a predictor of Legionella pneumophila occurrence in water samples. So with that, I'm going to turn it over to Gary to talk about our workshop.
Thank you, Mark. So before we were able to convince most of the utilities to begin collecting samples for Legionella where it's not required, we had to develop a response to detections that would be agreed to. So we held 2 workshops. The first workshop in May 24th of 2022, where we gathered more than 50 participants, including representatives from water utilities, regulators, academics, consultants, and professional organizations, to draft up, a basic schematic of what a response would look like when you get a positive sample detected. And then once that was developed, we had another workshop in July 13th of 2022, with the Association of State Drinking Water Administrators, so your state regulators, to look at that response protocol and say, look, if a utility is using this response protocol in your state and they got a positive, would you agree that this was a reasonable protocol to follow? The protocol then ended up being in 2 parts. First, the flow chart, and then once you get positives, a response table to follow that. And here's what it looks like. A lot of detail in here, but I'm going to walk through it in brief. You'll be able to see it in detail in the report. One thing to note is there's a lot of similarities between the detection of a positive total coliform or E. coli sample and what we developed for the response to a positive sample tested for Legionella. And you'll see that. And that helps because a lot of what we're developing is not really new. It's just within the context of Legionella. So you get a single sample positive. You collected a sample, some days later it comes up positive. What do? Similar to total coliform and E. coli, you assess QA/QC. You ask the lab, you go to the lab, did all the QC pass? Did you notice anything unusual? As Mark explained, did you look at the color of the trays? Was there something unusual there? Should we get a second opinion? But you also look at the sample collection site. Was there something going on at the sample collection site? Was maybe the tap out of order and a different tap was used, or maybe there was some maintenance going on that could have affected the actual sample tap location. And then finally, how was the sample collected? Were all the procedures followed for collecting a sample? was the sample handling and transport done standard practice. Next, you get the Legionella positive sample and other analyses we could do to get a little more data out of this positive. We would process it, send it somewhere to process for serogrouping. With total coliforms, you might run an API test and look at, is it Klebsiella citrobacter, what coliform genus and species could this be? And that may give you some more information, maybe not immediately, but maybe in the long run as you collect more and more data. Next, you decide, let's go back and take a repeat sample. We had a sample location that came up positive, again, similar to total coliforms. Was that just here today, gone tomorrow positive? Or could there actually be something going on related to that sample type, that location? Let's go back and collect another sample and see how that sample comes up. And in doing that, you get data from the initial sample, you get data from the repeat samples, and now we go to the response table and look at what do we do now with this information. And so the table's one continuous table, but I broke it down into sections. First, as Tim said, we have a baseline of Legionella. The water's not sterile. Legionella could pop up every once in a while. Same with total coliforms. Total coliforms are out there. You disturb pipe, disturb biofilm, you could get coliforms popping up in your samples here and there on occasion, usually very transient. We understand that. We get a positive sample. You look at water quality data. What was the chlorine residual, turbidity, anything else that could associate with that? And then you record the results and say, look, let's keep an eye on this. There's nothing maybe I need to do right now, but we'll keep an eye on the data as more rolls in. Now with Legionella, we have from the LegiAlert kit, we have both the abundance or density of Legionella pneumophila that was detected, as well as how many samples for a month or a day, depending on how many you're collecting, came up positive. And so based on those two things, if we get an elevated count greater than 100 mpn per 100 mLs, in this response protocol, we considered that, a little bit elevated above baseline. You go back, take a resample, you continue to track it. That's the original sample, the resample. You keep an eye on it, keep tracking it. And maybe you look at some other things. Was there construction going on around the area? Is there anything that could be obvious that could explain that? If you start to get not just one sample turning up in a month, but say you had 3 or 5 samples turning up either in the same pressure district or across the system, you might want to take a broader look at what's going on. So we're looking at both the MPN count and how many samples are turning up positive. Now, if you start to get samples that are greater than 1,000 per 100 ml, we really feel that at this point with the data that we have, that starts to get a little unusual and above the baseline where you might want to take a little bit more action. Of course, resample within 24 hours, look at your water quality data, and maybe even look at some of the controls you have. If there was water main work going on in the area, maybe you want to get out and flush. Check the disinfectant residual. If it's running low, maybe you want to boost it up a little. That could be by valve changes or flushing. Maybe there are some easy, common sense, low-hanging fruit type of actions you can take in response. At this point, you have to decide, what agreement do you have with your local health agency or your primacy agency? And are you reporting that data up the chain of command? Are you sharing that data and getting agreement on your response and how you're keeping an eye on the data and the conditions? Now, if you get above 1,000 per 100 ml, we feel in this response protocol with the data that we have to date, that's quite a high level, and that probably requires more serious action. Now we're getting into, with the lower levels, we may do like a level 1 assessment, like you would do with under the revised total coliform rule. You get up to the higher levels, a level 2 assessment, and a lot more immediate action. You're looking for a deficiency, and a deficiency where you can apply corrective action and see if that takes care of it. At the same time, you're communicating with your primacy agency and up the chain of command to make sure everybody's familiar with what you're detecting and how you're responding. Again, a lot very similar to what you would do for total coliform and E. coli. So the response to detection of positives follows existing Safe Drinking Water Act requirements. Communication is very similar as under the revised total coliform rule. We're not trying to create something different. We're trying to stay within what we're comfortable and used to doing and familiar with. Repeat sampling, sample location and sample collection quality checks, laboratory QA, QC, and a review of other associated water quality data. Or maybe you get the first positive, and then you say maybe there's some additional data we'll collect on the repeat sample. Follow-up actions, depending on the quantity that you get of Legionella, you can follow the RTCR level 1 and level 2 assessments. You should be familiar with them. They lay out pretty much what you would do looking for Legionella at the same time. Again, the purpose to identify any deficiencies and take corrective action and document that. Action includes maintaining a detectable disinfectant residual as required under the surface water treatment rule or your state primacy agency, and then, keeping the primacy agency in the loop so they're not surprised by anything down the line. So that's kind of the layout that we developed for the response protocol. It went well. Everybody seemed to agree with it. It seemed to make sense. And it was a good place to start and get everybody on board so that they could take the next step and begin monitoring. So now I'll turn it back to Tim, and he'll discuss the results now.
All right, thanks a lot, Gary. The results and analysis section, there's a little something in this for everybody. We're going to have results that are pretty easy to understand. We're going to have things that the modelers out there are going to love and everybody else is going to hate. So we'll first talk about the final data set. I'll give you an overview of it, some summary statistics. We're going to compare study years 1 and 2, and you'll see why that's important. We'll talk about the sample collection location characteristics. As Gary noted, your results could vary depending on the how and where the sample was collected. We'll talk about how different utilities varied with respect to their baseline, and I'll actually present. Gary was the one who came up with it, so a definition of baseline. And then we'll talk in some detail about disinfectant and water temperature impacts on Legionella pneumophila occurrence and abundance. And I'll take a moment to say occurrence, as I use it here, is the proportion of samples that is positive. So it's just any positive, no matter what the concentration, that's an occurrence. The Legionella pneumophila abundance, and I might in some cases use the word concentration, that's in a positive sample, what the count, how many Legionella bacteria per 100 milliliters or whatever the unit is. I actually took this out of the presentation. We're going to talk very briefly about Legionella pneumophila, a correlation with other water quality measures. And the spoiler alert that this would be very brief. In fact, I took it out because there is no correlation. We looked at things like HPC and other water quality parameters, and it's like most other people have like everybody else has seen. If you want to know what Legionella pneumophila concentration is there or whether it occurred, you got to look for the Legionella pneumophila. So we'll start with the final. Oops, I think I might have done. Let's see. Hopefully you're seeing the slide I'm seeing. The final data set summary statistics. The punchline for this whole study is that of 9,181 samples collected, and this includes some studies, some data from a study that Mark did previously, 1% of the samples was positive. So, hopefully everybody in the drinking water world is breathing something of a sigh of relief here. This was an exhaustive study. Yes, we used kind of the star students as the utilities that we sampled, but the percent positive was really low. If you look at the percent positive between free and free chlorine and chloramine systems, not a whole lot different. Statistically, there was a difference there, but it wasn't huge, and so it's nothing to write home about. We had 57 utilities all told. 25 of them were free chlorine systems, 32 were chloramine systems. Of those, there were 11 systems that had positives and were free chlorine systems, and 7 that were chloramine systems and had positives. That is, there were quite a number of samples or utilities that had no positive samples. So we find that the positive samples are not evenly distributed throughout the utilities, but most utilities are prone to having positive samples if you collect enough samples in those utilities. Positivity by sample collection location type. And I'll credit Randy McEwen, who also worked on this project and maintained the data. Randy painstakingly worked with the utilities to characterize each of the sample collection location types as either a building tap, so you're in a firehouse and sampling from a faucet near the point of entry on the building, a dedicated sampling station, and the definition of dedicated sampling station was left to the discretion of the utilities, a fire hydrant or a hose bib. You can see that by far the majority of samples were collected from what utilities designated as dedicated sampling stations, and they're really, when you break down the statistics and understand that there were few samples collected from fire hydrants and hose bibs, there wasn't a huge difference between the different sample location types. We do see high numbers from fire hydrants and hose bibs, and I guess it's not really a great plan to sample from those two types of locations for many reasons that I'm sure everybody in the audience is aware of. So sample location type is important, but mainly because if you're developing a monitoring program, you should be aware of the sample location type and the fact that it might have an influence on the Legionella that you detect or don't. Water age and Legionella pneumophila concentration. The plot on the right shows the Legionella pneumophila concentration in MPN per 100 milliliters, because the Legion Alert assay is 100 milliliters that is assayed. You can see for only positive samples, the estimated water age is on the x-axis, and the concentration of Legionella in the positive samples is on the y-axis. We didn't have water age estimates for many of the data. In fact, only 22 out of 107 positive samples had water age data associated with them. There is an apparent trend in Legionella pneumophila concentration with increasing water age, but we have to take this with a grain of salt. Too few data, and it makes sense that there would be a trend with increasing water age, but it's going to be correlated with a lot of other things. What type of pipes are in the distribution system in the vicinity of the sample collected? What's the disinfectant residual there, et cetera? In future studies, hopefully people will be more successful than we were in getting the water age data, and monitoring really should emphasize high water age locations. So comparing years one and year one and year two. On the left side, there is a table that shows in gory detail the statistics for years 1 and 2. And on the right side, I'm going to talk about that first. There's a plot showing the abundances, the concentrations that we observed in samples in years 1 and 2. In year 1, we saw, let's see, I don't see the number, 44 positive samples altogether. And you can see that there was quite a wide range of concentrations, going up to about 250 per 100 milliliters. In year 2, we had many fewer positive samples. There were a few utilities that were positive in year 2, but not year 1. But most of them were positive in both year 2 and year 1. And most of the utilities used the same sampling locations in both years. But you can see not only were there fewer positive samples in year 2, but the concentrations in the positive samples were less. All right, so let's talk about why that might be so. This is an interesting result. Could it have been because the disinfectant concentration and water temperature was different in years 1 and 2? I did a painstaking analysis, and the statistics say nope, they were roughly the same. Those two predictive factors were roughly the same in years 1 and 2. Was it because there were different sample locations chosen in years 1 and 2? Well, most of the utilities used the same sample locations in years 1 and 2. So our conclusion, this is a hypothesis, we don't have data to prove it, is that the explanation for reduced occurrence and abundance in year 2 compared with year 1 is that the utilities responded and did something positive. They did something to better manage Legionella in their system. And they did that because they monitored and they knew that that Legionella were there, and that there was an opportunity to improve water quality. In both years 1 and 2, and Mark will talk about this later, there were never the concentrations in the samples were never high enough to pose an unacceptable acute health risk, and Mark will tell you what all that means a little bit later. The concentrations were always quite low relative to risky ones. Utilities with positive detections or positive samples, they did follow-up monitoring. They instituted mitigative and protective practices like Gary was talking about, and it appears that those are the actions that caused year 2 to look better than year 1. And this is a success story. This says, hey, utilities, if you do monitoring and you supplement your water quality management activities to directly address Legionella, you can make a difference. Let's look at the difference between utilities. On the right-hand side, the plot shows that the bars are the percent positive samples, the kind of the occurrence for the utilities that had positive samples. And hopefully you can see it well enough. We have the number of samples in the labels in the x-axis, and the bars show the I think it's the 80%. Yes, it is the 80% confidence interval around that estimate. 18 out of 57 utilities reported at least one positive sample. The proportion positive among utilities reporting at least one positive sample was between 1 and 15%. And generally, we saw higher proportions positive if utilities collected fewer samples. And this is a pretty simple statistics hurdle to jump over. If you have fewer samples, one positive sample is going to make you look much worse than perhaps you are. So it's an indication that more monitoring is needed. And yeah, maybe you do have 15% positive, or maybe you have sites that you need to address, and your overall positivity rate is not that high. We're gonna take this one step further and think about a baseline occurrence. And I promised to tell you what baseline is in the next slide. I calculated, or we calculated, the 50% upper confidence level for the proportion positive for each of the utilities. And that includes utilities that had no positive samples. It's possible that you could have no positive samples but still have Legionella in your system. You just didn't collect enough samples to find them. And so we have all of the utilities in this plot, and we're showing the 50% upper confidence level for the proportion positive. The data seem to group themselves pretty nicely into two bins. There are data that indicate what we think is a baseline occurrence. This is just what you have at that utility given the conditions. And then there were some outlier utilities that had much higher percent positive. Generally, these had fewer samples, and they were reduced in subsequent years. So right now, with the data we have in hand, we would say that if a utility were to decide to go out and monitor, it is possible that they would have, roughly 5% positive samples and just be in their baseline condition. If you get higher than that, then there's probably some specific problem that needs to be addressed. So baselines, as promised, I'll credit Gary with coming up with this definition. We're calling a utility baseline for Legionella pneumophila the occurrence, that's the percentage of positive samples, and range of concentrations for samples from locations that are representative of the utility's distribution system. That's where they are as they're currently operating. Utilities all have different baselines for Legionella pneumophila. They have different source waters, different primary and secondary disinfection, different system characteristics, things like unlined cast iron might make a difference, the configuration of their storage and maintenance, and other factors. So this baseline isn't really a national baseline. It's a baseline that a utility can establish and say, okay, here's where we are right now. Can we make improvements in our management of Legionella? And that's also, if they go outside the baseline, hey, do we need to make some changes in our operation? The differences in the baseline, it doesn't mean that some utilities are inherently risky or poorly operated. All of the utilities have concentrations way below anything that would be likely to make somebody infected, much less ill. It's just a reality that treated water isn't sterile, and the ecological conditions specific to the utilities are going to determine the degree to which Legionella pneumophila is present at the low levels that we observed. All right, on to some somewhat busy slides. Sorry about that. Let's look at Legionella pneumophila concentration abundance as a function of disinfectant residuals. So on the right-hand side, the top panel, the dark dots show positive samples, and they show the concentration in MPN per 100 milliliters. And then the x-axis is the disinfectant concentration. You can see that we saw disinfectant concentration for free chlorine systems from 0 to just a little bit above 2, but they were really mainly clustered around 1, along with the samples. There is the highest samples and the highest occurrence all occurred down near 0 or approaching 0.2. And so put that in your memory, because we're going to come back to that. So if you have low concentration, you have both high likelihood of occurrence and you have high numbers when there is an occurrence. The bottom graph shows the same type of data for the chloramine systems. The non-detects are shown as the lighter colored dots, and the darker dots show the detections. And you can see that the detections are somewhat clustered around, the 0 to 0.2 neighborhood for total chlorine. But there are detections for both the free chlorine and the chloramine systems going way up. In fact, we saw a detection at a total chlorine concentration of 3. What does that say? Well, sporadic high, where high is relative to baseline, not high relative to being risky. High Legionella pneumophila concentrations occurred above 1 milligram per liter, both disinfections, because disinfectant is not a silver bullet. If there's something, if there is a system deficiency that is not disinfectant, not missing disinfectant, if you don't address that deficiency, you can increase the disinfectant and still have Legionella pneumophila. So multiple barriers remains the right approach, even for a latent risk like Legionella pneumophila. Concentration versus temperature. We had a little bit surprising results here. The top graph is similar to the plots that I showed in the previous slide. In the top graph, we've got temperature in degrees Celsius on the x-axis, and then Legionella pneumophila as MPN per 100 milliliters on the y-axis. And again, the light colored symbols show non-detects or below detection, and the darker symbols show detections. Contrary to what we expected, there were a number of detections down in the low temperature range, between 0 and 10 Celsius for one utility. So that was a bit of a surprise, but look at how low they are. They are very low numbers. So this gave us a bit more information that hey, there are detections at concentrations low, or at temperatures lower than had previously been thought. but are they of consequence? That's a question for the community to take on. But you can see that there are very few data above a concentration or above a temperature of 30, but you can see a trend toward increasing positives and increasing concentrations as you increase the temperature. It's much clearer for the chloramine systems. We didn't see any detections below 16, I think it was, and we saw increasing frequency and concentrations as the temperature was increased. All right, here's a slide that all of the modelers are going to love and the rest of you might hate. We looked at the distribution of Legionella pneumophila concentration within all of the samples. We fit the data to various statistical distributions, and the log normal distribution fit the data best. And you can see the statistics here and plots, and yeah, the data do look log normal. We looked also at Weibull normal and I think a couple of other distributions. So I won't go into this in great depth. We do go into it in great depth in the report. But for those of you who are trying to think, okay, what's the national risk or what are the national trends in Legionella pneumophila concentration? Hopefully this will get you at least started with that thought. Let's talk about Legionella pneumophila occurrence and control and distribution systems. The primary factors and the ones that we focused on in this study that are related to Legionella pneumophila occurrence and distribution systems are water temperature and residual disinfectant type and concentration, and then other things that we've already talked about or that we weren't able to measure: water age, pipe material and condition, sediment accumulation, distribution system integrity, etc. And these factors are all coupled. For example, high water temperature is associated with greater disinfectant decay and severe nitrification. So you have to think about the water temperature and the residual disinfectant type and concentration as a package. And another example of this: old unlined cast iron pipes are going to exert a different disinfectant demand and generate corrosion products. So that factor then is coupled with the residual disinfectant type and concentration and should be considered together in analysis. All right, take a look at the factors that are associated with occurrence and control of distribution systems. As Gary pointed out already, most of these factors are addressed in the RTCR or for other requirements and for within utility biological water quality management. So we're not talking about something totally foreign and new. We're just putting a different spotlight on a contaminant and trying to address it specifically within the context of water quality management as is already practiced. Skip too far. The last kind of geeky slide that I need to show before we get into the big punchline for the results is it relates to disinfectant concentration correlation with water temperature. As I pointed out, temperature and disinfectant are related to each other. So if we're thinking about modeling, we have to say, all right, to what extent are those related to each other, and how does that need to be considered in the model? And if you want the gory details, they're in the report. But essentially, if you look at the entire data set, we see weak or no correlation between temperature and disinfectant over the entire data set for both types of secondary disinfectant. We did see significant correlation at the utility level for some utilities, but not all utilities. So that introduces the next slide, which is the logistic regression model we use to kind of pack everything up and come up with some results on the occurrence of Legionella pneumophila and what temperature and concentration have to do with it. We developed a Legionella pneumophila occurrence model that was logistic regression. We think that's the best approach because other approaches might rely on some arbitrary bin size selection, and I'll tell you what that means in a slide or two. It includes both temperature and disinfectant together as they need to be. we fit this logistic regression model to the data, and we had mixed results. For the free chlorine systems, recall that there were a fair number of positives at very low temperatures in the free chlorine systems, and we only found that the disinfectant residual concentration term was significant in the model. So you'll see those results look a little bit different from the chloramine systems, in which both terms were significant. Free chlorine. So let's look at the pictures first, and then we'll go through the results. In the upper right-hand side, you see free chlorine on the x-axis and the proportion positive on the y-axis. There are, I don't know what color that is, salmon bars that are arbitrarily width. We decided to make them each 0.2 chlorine units wide. And that's an arbitrary decision, but it shows the data reasonably well. The black dots show the positive samples, and the lighter dots show the non-detect samples. There is a somewhat fainter than I probably should have used line that shows the logistic regression model fit, and it does a pretty good job of following along the bins that we chose arbitrarily. So that's the logistic regression model showing only the free chlorine impacts. Because the temperature term was not significant, we are showing the temperature impacts separately in the bottom figure. The bottom figure, we bin the data somewhat arbitrarily in roughly 8. Well, in intervals that had roughly the same number of observations in each bin. And we can see that there was a fair number of positive samples observed at but low concentration at low temperature. But if you neglect those, there's a general trend toward increasing positivity as you increase the temperature. Chloramines, we got a much prettier picture. So let's walk through the figure on the right-hand side. The x-axis is the total chlorine concentration, and the y-axis is the temperature. And so both the chlorine concentration and the temperature figured into the model. The lines show lines of iso proportion positive. So up in the upper right-hand side, about 4% positivity when you were above 36 degrees and up to 40. That's something of an extrapolation there. And you can, as you move to the right, you can see that the total chlorine concentration increases. You can see that the proportion positive decreases. We found, you can see that the spacing between lines of iso occurrence increases with increasing disinfectant concentration. That is, there are diminishing, just like the free chlorine systems, there are diminishing returns as you increase the total chlorine concentration. And that's because you're treating something that is not the root cause. You're adding total chlorine when in fact it's something else that is harboring and causing the Legionella to grow. Temperature effects are less important than disinfectant residual. You can see how steep these lines are. And so, but it's intuitive to control to a target occurrence level, if that were your objective. You need to have higher residual disinfectant concentration as your temperature increases. Few caveats and the to-do list. The caveats, the model was developed using pooled data from all of the systems. As you see, there is a baseline for different utilities, and that can vary. So, a next level of modeling could separate out the utilities and do similar statistics. We know that many potentially important factors are not present in the model. The pipe type in the vicinity of the positive, et cetera. And as you're probably tired of hearing, disinfectant is not the silver bullet. There's a to-do list here. I invite anybody else to analyze these data. I'll see what I can do as well. Definitely need to collect and analyze more data, including the contextual data. What was the sample tap type? What was the disinfectant concentration? What were was it near storage, et cetera? These data could be analyzed with system as a factor. They could be reanalyzed with removal of some of the data that have confounded the analysis. and they could be also reanalyzed with the very low concentration data removed, because those are somewhat unimportant. All right, next, Mark is going to talk about risk benchmarking.
All right, thanks, Tim. So we want to know, well, what does all this mean? And so just to kind of recap what Tim just showed us, we had 57 utilities, we had almost 9,200 samples, 1%. Importantly to say that from 18 utilities, so 32% had some detections, 68% had no detections. The counts range from 1 to 267, and that's shown here. Kind of emphasize that, put in the context that Gary had talked about. The concentration is less than 100 per 100 mil, or less than 1 per mil. You can look at the data both ways. Most of our results, so in fact, only 5 samples out of almost over 9,000 samples were above that kind of trigger level where it would trigger some additional follow-up and flushing. And then most of these are repeat negative. Now, some of these the samples above 100 per 100 mil came from the historical data set. A couple came during this project. When they did get that and then repeat that repeat sample was generally lower. Pointing to what Tim had said, is once utility is aware and kind of that follow-up can help manage Legionella. So I'm going to put this into a risk model. This was a model was published by Carrie Hamilton in 2019. And I'm just going to step through the model because it's not very familiar to a lot of people in the water industry. So the first aspect of the model determines kind of the route of exposure. So Carrie looked at whether faucets, toilets, or showers, aerosols that came from those devices, whether they were conventional or high efficiency, kind of the idea, well, maybe high efficiency toilets had less aerosols. So, we looked at all of that. I also put that in context of CSI. Now, that is not the television show. That stands for clinically significant illnesses, or think about that as people with Legionnaires Disease. And then both also looked at the results on a per exposure basis. So if I get a single result and I want to know, well, what does that mean? What's the risk of being exposed to that one result? The analysis was done in that way, but more commonly, which we do for Giardia and Cryptosporidium viruses, we express that on an annual basis. So has that annual risk of getting Legionnaires disease. But also, to account for sensitive populations, EPA uses in the regulation, well, what's the risk of infection? Because the outcome of an infection can result in disease or not, depending on your immune status. So to account for immunocompromised and sensitive population, EPA uses in the rulemaking, what's the risk of infection? And again, we can also do that on a per sample. So what's my probability of getting infection or disease? And you can see that the difference between the two is about 2.5 logs, or about 100, between 100 and 1,000 times more concentration to cause a disease than it does just to cause an infection. Again, both for per exposure or per annual. So all of these factors are kind of rolled into the risk model. Now, we have to make some assumptions, and these are important because we measured Legionella in the distribution systems, not in the buildings. And even where samples were collected from sample taps, they were flushed for 3 to 5 minutes, so that we were intending to monitor the water from the distribution system. So we have really no data. This project doesn't say anything about Legionella in buildings, but that's where you get exposed. You tend not to take a bath, take a shower, use the toilet out on the street corner. You do that in kind of buildings. So we have to assume that the water quality that we measured in the distribution system remained unchanged until the point of exposure when we do these kind of risk calculations. And so this is done for the data we show here are for the 6 utilities that had the most Legionella occurrence. Now recall 68% of the sample utilities had no results, no detection. So first of all, to say that when we put all of this data into an exposure model, the risk model, all the risks were below that 1 in 10,000 annual risk of infection benchmark that EPA uses. In fact, the systems with the 5% kind of baseline that Tim had talked about are about 2 logs below this risk level. And of course, the national exposure would be even lower than that because 68% of the utilities had no detections. So we can conclude based on this data set that the overall national exposure is very low for utilities that have a higher occurrence, greater than 5%. We have higher baseline risks, but still all of them were less than that 1 in 10,000. And even the highest concentration, which was 267 MPN per 100 milliliter, when we put that into the single sample exposure, was less than a 1 in 10,000 risk of infection based on that one exposure. So we think that these data are good for utilities because it says it opens the door to utilities doing monitoring, managing the occurrence of Legionella, most of the time below 1 per mil or 100 per 100 milliliter, and being able to see that occurrence and manage that by flushing and managing disinfectant residuals and doing all the things that Tim had just talked about, and still have a management plan for Legionella that are still way below the kind of risk thresholds that we would commonly use for water regulation. So with that, let's move to some conclusions, kind of blow through this. It should be fairly obvious that overall this project found Legionella levels at low at well-run systems. Of course, we don't know what happens in poorly run systems. That would be an additional study. The result of this project showed that monitoring worked. More than 50 utilities collect samples over 2 years. So it says utilities can do this. It's feasible for them to do that, and they can do it in-house, and they can, based on that data, they can better manage their distribution system. A protocol was developed for this project to help them in helping them manage the systems. But we need to have ultimately the buy-in by EPA and health agencies and regulatory agencies for more widespread monitoring. Right now, this is just what these researchers thought was kind of a good idea. And as we've talked to regulators, you can like this, you can hate it, you can propose something else, but utilities are monitoring, and we need to have some kind of framework to evaluate those results. And so, this is our best shot at putting that framework together. Disinfectant residuals are not a silver bullet, but that being said, maintaining at least a 0.2 milligram per liter residual in all parts of the system was beneficial. Maintaining residuals at higher levels, greater than 0.4, had no substantial benefit over maintaining at least a minimum residual. Now, this helps manage Legionella and distribution system. It's not necessarily intended to say that this residual will help manage Legionella in building systems. And the study showed that a minimum of 0.2 was the same for both free chlorine and chloramine. We don't find necessarily the scientific basis that chloraminated systems have to operate at a much higher level. In fact, a lot of research has shown that chloramines, in fact, are particularly beneficial for managing Legionella. We think there's some mechanistic research why that may be the case, and that studies particularly, because we focus on Legionella, not the amoeba that Legionella grows in, the disinfectant residual, we have an opportunity to basically understand why chloramines are so effective. And I'll turn it to Gary to kind of give some recommendations.
Okay, let's run through some recommendations. Of course, researchers wouldn't have fun unless we could apply what we've learned. So utilities can and should proactively manage Legionella pneumophila. Now, the good news about that is we're already doing much of that to begin with. We already manage Legionella pneumophila probably indirectly. Most utilities have activities that promote that management, especially under the revised total coliform rule, nitrification control programs, and other water industry best practices. So the multiple barriers should already be in place for much of what we've been talking about and what we need. And as Mark has said, we're able to monitor for Legionella pneumophila. So let's go out and collect the data. There is no surrogate parameter that can substitute for Legionella pneumophila. You can't collect total coliform data and then relate that to what's happening with Legionella pneumophila. And HPC bacteria tell us maybe about what's happening in the system, but not directly about Legionella. So we need to go out and take routine samples. And we have the method to do that. And we need that baseline data to understand our systems better. For Legionella pneumophila management, utilities should maintain a minimum disinfectant residual of at least 0.2 milligrams per liter for chlorine and chloramine. It's a good starting point. But as Mark said, remember the chlorine residual is not the magic bullet. You need the multiple barriers in place. However, being able to maintain a minimum disinfectant residual tells you a lot about how well you're operating and maintaining your system overall. And that overall maintenance and operation are good practices for minimizing Legionella pneumophila. And we need regulators to develop consensus on reporting and communication requirements to encourage utilities to go out and collect the data and respond to it. A lot more states need to develop reasonable reporting and monitoring agreement for collecting that data. We're lacking that. We're lacking good guidance or infrastructure for assisting utilities in that. Some of what we did will help with that, but as we collect more data and get more case studies underfoot, we'll be able to develop even more solid response protocols and so on to address Legionella. Because there's so few Legionella positives, as you saw in this study, we need a large database to really understand what's going on with Legionella pneumophila, not only within a utility, but across the nation. And one of the ways to do that, one of the ways as researchers we think, is to have utilities collect the data and submit it to a centralized database where we can anonymize, the database so you don't know which utility it is, but you can collect associated data and start to make correlations, and that's the ideal situation we would like to be in. Well, what are some final thoughts on next steps? Well, more research is needed to better define baseline occurrence and what constitutes whether a distribution system is in or out of control. We especially need data on case studies where controls have been applied to mitigate elevated occurrences, and we can see what works, what doesn't, how well does it work. We also need data on case studies of when things go wrong, when a storage tank goes bad, when there's a water main break. Can Legionella intrude into the system under those conditions? The revised total coliform rule is a good example of how we can develop a monitoring program for Legionella pneumophila, but we need to incentivize utilities to collect the data. The current MCLG of 0 for all Legionella species, including Legionella pneumophila, is actually a disincentive. Now, that was developed back in the 1980s before we knew all that we know today, but we need to bring things up to speed today and adjust that if we can. And finally, knowing how little we still know, we need to advance in reasonable steps based on sound science, so that we don't paint ourselves into a corner. So we have to be careful on as I said, on the monitoring requirements, the reporting requirements, regulations, standard practices, so that we don't drive utilities to to not want to collect data because they're worried about the implications of having a positive. We need that data. We need those case studies to move forward. And we'll go to Q&A.
Well, thank you so much for our speakers today and great presentations. So we're going to kick off the Q&A sessions. As you see in here, so we have only 10 minutes, so I don't think so we can go through every question that we receive, but we'll try to do our best. So the first questions, there's two questions about the limit of quantifications. So I'm going to I'm going to combine those two questions and ask maybe this question's for Mark. So could you please tell us about the limit of quantifications of the Legionella method? And then also another question is which sample volumes was used for the ISO 11731 method?
Yeah. So we presented the Legionella it can be done in two formats, the 10 mil format and 100 mil format. We use the 100 mil format, so nearly all the data were collected in the 100 mil format. So Legionella, it's very easy. It's Legionella per 100 milliliters. The ISO method collected 250 mils, and that was concentrated down. There was a question in the chat, and they used both an acid and a heat treatment as well as direct plating. So Q Laboratories is excellent. They do the full ISO method. A lot of laboratories kind of cheat by only using part of it. Every sample got plated directly and with heat treatment and with acid pre-treatment to try to detect Legionella by the ISO method. The concentration on the qPCR, the viability qPCR, was also based on 250 mils. It was concentrated, but the results were expressed as Legionella per 100 milliliter. I think that the detection limit was maybe like 5 genomic units per mil. I'd have to go back to the report, but still, they were large volumes. We knew that we wanted to compare apples to apples as best we could, given those three methods.
Yeah, well, thank you. Maybe there is a couple of questions about the Gary, so you present a table of actions. So I'm going to ask those questions. So, and then you show the table of actions, and then you show the MPN. So is MPN equivalent to the CFU-ML? And then that's the first question. And then second question is, would it take a regular BAC-T test will be helpful when resampling for the Legionella? Gary?
I'll let Tim or Mark answer the CFU versus the MPN.
For our purposes, equivalent.
Okay, thank you. How about a BAC-T sample? Anyone would like to take?
Well, you know, similar, if I understand the question right, similar to taking a total chlorine residual sample and maybe a turbidity sample, a general BAC-T sample, whether it's coliform or HPC, tells you a little bit about what's happening in general in the system. But what's happening in general in the system, like long water age, maybe a disruption, doesn't necessarily tell you if Legionella is going to be present or measurable in that sample. You know, we do need to control the system overall for a variety of reasons. And right now, with the data we have, we can only assume that the management of a good system and good water quality will also control Legionella. As we gather more data, we'll better understand how that relationship plays out.
Anyone would add? Okay, well, thank you. So another question, maybe this for Gary as well. Does the response protocol include the reporting to the public or just to the regulatory or health agency?
Yes, good question. The way we developed a response protocol is to leave room because some states already have response requirements in place. So we're trying to encourage the dialogue between the primacy agency and the water utility, and hoping with the information we provide, that dialogue will be a reasonable and healthy dialogue. But the bottom line is now, without a federal requirement, each utility has to really work out with their primacy agency, how they want to handle positive samples, and when in fact public notification or local notification of the customers would be required.
Thank you. Well, this question's for the team. So since majority of the sample, your slide 38, maybe I can change the slide here. Bear with me, 38, sorry. Okay, this one. So since majority of the samples are from the dedicated stations, so what do you think this data says about the concentration in premise plumbing? Does this give a false negative impressions?
I wouldn't call it a false negative. The way I think of the two parts of Legionella exposure, there's the utility part and the building part. The decisive part is the building part. You can provide a building with very low Legionella water and very high residual, but if the building isn't managed to control Legionella, then all bets are off. You can have a very high concentration there. So in a big sense, if you have fewer Legionella in a sample from the distribution system, you're seeding buildings less frequently, and you might think they would have less positivity, lower numbers. But I'm not sure that really plays out. There have been a number of studies that have identified things like age of plumbing materials as being a highly predictive factor for Legionella occurrence in buildings. That has nothing to do with the distribution system and the water supply. So the two pieces are related, but control needs to be maintained on both sides of the meter.
Just to, Grace, I'll take, just to kind of be clear on this, the focus of this study was the distribution system. So we did no building analysis, and any sample taps that were collected in the building were flushed for 3 to 5 minutes so that we had water from the distribution system. So, the focus of this was not at all on the building, was trying to understand what we know about distribution system. But just to underscore what Tim just said, I'm involved in a utility that's had an ongoing outbreak of Legionnaires disease. They monitored their distribution system. Probably close to 100 samples of distribution system have been negative, and yet building levels were high, sometimes well over 1,000 Legionella or 2,000 Legionella per 100 milliliter. So Legionella was amplifying in the building, but very low or undetectable in about 100 sample collection in the distribution system. So there are two different environments. We believe the reason for doing this project is we need to manage both. But this is the part of the utility that the utility can manage. So, the focus of this research is to provide guidance for that aspect.
Excellent. Thank you. Another questions. How did you estimate water age in those sampling points? Anyone will take this one? This question.
That was the estimates were made by the utilities, and I don't know the methods that they used. The utilities were great. We relied on them for doing everything from collecting the samples to estimating water age and so on.
Excellent. There is another question about the false positive. So is there any false positive? If so, were they included in the positive count?
Yeah, I'll answer that. To try to go back to that slide, I said 96% of the Legion Alert trays, we were able to isolate Legionella pneumophila from that tray. So, we had a 96, you could call it 96% confirmation that was that they were there. For purpose of our research project, we only used counted positives, the trays that we detected Legionella pneumophila in there. But I made that point that, for that 4% that was different, it wasn't a big difference. The concentration and overall percent occurrence, the overall concentration would not have looked any different than what we had. So any kind of, we're not saying that those 4% were wrong. We're just saying for our project, we required, for our research, we required the detection. So, that 96% was the confirmation rate.
Okay, well, thank you. Well, so now it's at 2:30 at the Mountain Time, and obviously we couldn't get through all of your questions. So we're going to follow with answers afterward. So again, a big thank you and to our speakers and everyone who joined us today. And we hope that you found that this webcast both informative and helpful. So if you like to access the final report, and please go to the foundation website and type in 5156. Again, thank you so much for your participations, and we look forward to connect you again, and have a great rest of the day. Thank you.